In this section, we will discuss probability. Probability describes how likely something is to happen. Its probability occurs on a scale of 0 to 1. 0 being it's impossible, it won't happen, to 1, it will definitely happen. If we were to put that in terms of percentages, it would be 0% impossible to 100% absolutely certain. We describe probability in relation to events, the probability of an event or a single result occurring, and the probability is calculated by the number of ways a single event can occur compared to the total number of outcomes. So in the event of rolling a dice, if we wanted the outcome to be 5, well then we have one event. That event is rolling a 5. But there are 6 possible outcomes. We could roll a 1, a 2, a 3, a 4, a 5 or a 6. So in the event of rolling 5 and 6 outcomes, we have a probability of 1 in 6. If we were tossing a coin and we wanted it to be tails, well that's one event and 2 possible outcomes. It could be heads or tails. So our probability is 1 in 2. Tossing a coin 100 times and applying the probability of 1 in 2, we could expect to get that tails 50 out of those 100 times. But we may not get it 50 times. We are likely to see variation there where we might get 48 or 55 tails. This is natural variation in our probabilities. If we were to apply the logic of probability to our standard deviation chart, which tells us that 68% of the population should fall within one standard deviation of the mean, the probability of any observation falling within one standard deviation of the mean is therefore 68%. The probability of an observation falling within 2 standard deviations of the mean is 95%. And the probability of our observations falling within 3 standard deviations of the mean is just under 100%. This is the likely outcomes for an entire population of samples. Probability is often used in models. In predictive forecasting, we use historical information to work out what are the chances of something occurring or not occurring based on what has happened in the past. Such a model is yield profit, developed by CSIRO. It's an agricultural decision support tool that uses current day scenarios and probability forecasting. The model that it's based on is called APSIM, the Agricultural Production Systems Simulator, and it's used to produce predictive crop production tool using the inputs of various crops, pastures and trees, specific soil information related specifically to a paddock, and the management controls that have been applied to that paddock for stubble retention, erosion control, fertilizer management, etc. And it also uses the water balance with respect to growing season rainfall. So yield profit has a number of applications, not just directly to farmers, but also to decision makers and people within the supply chain, as well as policy makers for looking at wider broad-scale policy across the agricultural sector. So yield profit looks at paddocks individually. It takes the effect of environmental factors such as temperature, rainfall and frost conditions, as well as management decisions. How has the paddock been treated in the past and how has it been managed for this year, and simulates how those decisions and environmental factors will influence crop yield. So it First it takes the farm details. For the paddock location, it needs to know the paddock location when linking the information to the nearest weather station and to have the historical data from that weather station. It looks at the soil type and soil tests, and specifically crop types, cultivars and sowing dates. There's a huge range of crop types for which yield profit has been developed. So yield profit works by modelling the crop growth using the AppSim model. It uses up-to-date environmental conditions for growing season rainfall from the date of sowing. The reports are produced monthly at the end of every month, so you can see how your crop is faring and how the predictions are changing as your environmental changes occur throughout the season. It then makes predictive analyses based on 100 years of historical rainfall data for your location. It runs the scenario for your current situation through those 100 years of historical data and looks at, well, what are the probabilities of specific results and outcomes over those 100 years. So it's looking at the crop growth possibilities, the yield and likely maturity dates. We'll have a look at what the output looks like now. The output from yield profit is concisely presented in a report only a few pages long. What it will show you is the grain yield outcome, and what we have here is a nitrogen limited yield, and that's the solid green line, and then we have a broken green line which shows us how that yield will be affected with the effects of frost and heat included in the simulations. So what we can see is from the solid green line we have a 100% chance of reaching a yield ton of 2 tons per hectare. The probability on this graph is given on the y-axis, the yield is given on the x-axis. It drops off pretty quickly to just under 4 tons per hectare. So we have very little chance of achieving that in the current situation. But with frost and heat effects, we find that rather than having a 100% chance of reaching 2 tons per hectare in grain, we have only a 70% chance of reaching 2 tons per hectare. Similarly, we have water limited yield shown with the solid blue line. And then we have the decreased yield that we could expect if we were to include frost and heat effects on our crop during the growing season. This next slide shows us the hay yield outcome. So it's different from the previous slide which showed the grain yield. This time we're only looking at dry matter. So we can see from the green line, this is the actual yield available with available nitrogen to date. The red and the blue line combined is when the yield that could be expected if nitrogen was non-limiting from today forward. So we can see from the green line that it starts off with a hay yield of about 5.5 tons per hectare and drops down. We could expect a 100% chance of achieving 5.5 tons per hectare, but we can expect almost 0% chance of achieving just over 7 tons per hectare without additional nitrogen inputs. If we were to make nitrogen non-limiting, we can see that we actually have a 90% chance of achieving a hay yield of just over 7 tons per hectare. In this plot, we can see how the growing season rainfall is incorporated into the model. We have our rainfall given on our y-axis, the vertical axis, and then we have our months of the year given on the x-axis. Now we spoke about earlier about percentiles. Well, a percentile is where we break the data into 100 equal units. A quartile is where we break the data into 4 equal groupings. Well, a decile is where we break it into 10 equal groupings. So what we have is the red line, which is the lowest 10% of observations over that 100-year period. So the lowest growing season rainfall recorded. On the black line, it shows us the median growing season rainfall recorded at the 50th decile, or the 5th decile rather, the 50th percentile. And then finally on the blue line at the top, we have 90% of all rainfall observations occurring at this rainfall level. So we can see from our green line, our growing season rainfall, that the season started off quite poorly. It started off with a rainfall as low as the lowest 10 years within our 100-year period of data. But then it picked up in early May, and it's now probably up between 75 and 80% of historical records of observations. So it's become an above average year for rainfall. Now the predictions that we have seen for grain yield, for hay yield, and then incorporating growing season rainfall, Yield Prophet then makes predictions at when each growing phase will occur. So we have the different tillering stages of the plant. We have the flag leaf stages, and we have the head emergence, flowering, and then the dough fill stage, or the grain filling stage of the plant. What we can see here is that the green line shows us the predicted values, and we have the earliest date, the median date for the crop, and the latest date by which these stages will occur. The first 3 dates reports have already been produced for these first three dates, so they're not part of the predictive phase anymore. What we have then is at the 4th leaf tillering stage, we have the earliest date being predicted as the 4th of July and the latest as being the 9th of July. Within these probabilities, we only have a 5-day spread, so it's less than a week from our earliest to our latest tillering stage. Later on, towards the end of July and August, our 6th leaf stage, we have a 15-day spread. So we have greater variance in our predicted possibilities or probabilities. And finally, at the very end, between the 19th of October and the 12th of November, when we're looking at the mid-dough fill stage, we have a variation of 25 days in our model from which we could expect our earliest dough fill to our latest dough fill. So our predicted and our probability of our observations becomes more widespread the further out we are making those predictions.